Okay, so we're going to look at the main reactions of alcohols, and there are four of them that are in the syllabus. And two of these we already covered, which is dehydration of alcohols to make alkenes and substitution to form halo alkanes. So I'll do those at the end. Combustion is very similar to the burning of alkanes reaction, although the only difference is that you've got oxygen in the alcohol to consider when balancing the equation. And then we look at later oxidation using oxidizing agents such as potassium dichromate, and we get different products for different types of alcohols, different classes of alcohols. So for primary alcohols and secondary alcohols, you get different products. If we burn ethanol in oxygen through complete combustion, we get the carbon in the ethanol oxidizing to give us carbon dioxide, and we get the hydrogen within the ethanol oxidizing to give us water or steam, and we balance for those carbons and hydrogens as normal. And then we need to balance the oxygens, but just be aware there's oxygen in the ethanol here, so we need to make sure we account for that. So on this side we have 4 oxygens here and 3 there, that's 7. So we need 7 on this side. So 7 minus 1 from the ethanol means that we need 6 on here, so there's 3 there to balance. So make sure you never use molecular formula, so don't write C2H6O. Whenever we write equations for organic chemistry, we should really show the functional groups, and we must show as much structure as possible. So if you want to, show skeletal formulae in an equation, and that's fine. So never use molecular formulae, always show functional groups and as much structure as possible. So here we've got an example of cyclohexanol, and we can balance this equation using the skeletal structure of cyclohexanol rather than writing C6H12O, which would be the molecular formula. So in this case we have 2, 4, 6, 8, 10, 11, 12 hydrogens. So we're going to have 6H2O, and we have 6 carbons in the carbon ring, so that is going to be 6 CO2. And then on the right hand side we have 6 oxygens there and 12 there, so that's 18 oxygens. On this side we take 1 off from the alcohol, so 18 minus the 1 is 17, and 17 divided by 2 would be how we balance CO2. So you can make it quick and write a fraction like that if you want to, or you can write 8.5 O2. So we just looked at combustion of alcohols, which is a type of oxidation, but there's another way of oxidizing alcohols through the use of oxidizing agents, which is not burning the alcohol. We get different products in that oxidation. So we're going to look at that next. Okay, so we're going to look at oxidation of alcohols. So there's a lot of new content in this part of the topic because we have new compounds we need to know the structures of, and we need to be able to write certain equations in a new way, and so on. And we need to learn some new reaction conditions as well. So we're going to look at how we oxidize primary alcohols and secondary alcohols, and look at what the products are because they are different. So to oxidize alcohols, we need to use an oxidizing agent, and there are different types of oxidizing agents, but one of the most common ones we use for this topic is potassium dichromate. So I'm going to draw an arrow to show that we're going to use potassium dichromate, which is K2Cr2O7, and the active part of the potassium dichromate is the dichromate, that's the anion. The cation are spectator ions. So sometimes you see this written as instead Cr2O7 2 minus, because potassium, as we know, are single plus ions. So 2 potassium ions means that this dichromate ion is 2 minus. And you can work out the oxidation state of the chromium by using the rules from when we did oxidation numbers. And that's going to be +6. So you often see potassium dichromate written as potassium dichromate 6. As the Roman numeral, you may remember, follows the part of the name with the elements with the variable oxidation state, which is the chromium. So the 6 doesn't go here, which is for the potassium. Potassium hasn't got a variable oxidation state. Also, the potassium dichromate has to be in aqueous solution, and it must be acidified, so we must have protons in the solution. So we use aqueous acidified potassium dichromate, and this needs to be heated. So often we say this is hot aqueous acidified potassium dichromate. The potassium dichromate is a reactant in this reaction of oxidation. However, we don't write the formula of the potassium dichromate in the equation because it's actually quite difficult to balance using that formula. And all this potassium dichromate is effectively doing is providing oxygen atoms in the reaction. So what we do instead, we represent an oxidizing agent like potassium dichromate with this symbol, which is an O in square brackets, and that represents any oxidizing agent, and in this case it represents the potassium dichromate. So this shows the oxygen provided by the oxidizing agent, and we can then put a number in front of here to balance the equation later. If you oxidize a primary alcohol, you undergo a two-step reaction, and the first stage we produce something called an aldehyde. Now, we've not met aldehydes except at the beginning of the video when I mentioned aldehydes to make alcohols in the second year, but an aldehyde is this structure. So this is the aldehyde functional group. It's got a carbon, a hydrogen, and a double bond to an O. And this is the rest of the molecule, so this could be an alkyl chain. I'll write some examples of specific aldehydes later and name some of these aldehydes. Before we do that, we're going to look at how we can balance this equation, and it's quite simple because all we're going to do is look at the difference between the atoms on the left-hand side and the right-hand side. So on the left-hand side, we've got one carbon on both sides there. We've got the rest of the carbon chain, and on this side, we've got 3 hydrogens. On this side, we've only got 1, so there's a difference of 2 hydrogens missing on this side. So there's 2 hydrogens missing on here, and we'll list those there. And on the left, we've got 2 oxygens at the moment, and we've only got 1 here. So there must be something on here with 1 oxygen. So hopefully you can see that this is likely to be H2O. So this produces water in the first step of the oxidation. So if we leave the aldehyde in the oxidizing agent, and if there's any oxidizing agent left over, it will oxidize this further. So the aldehyde will undergo further oxidation with oxidizing agent to give the carboxylic acid. And the carboxylic acid looks like this. It has this structure. So I'm going to try and keep it in relation to this, the way I'm going to draw it. So we have double bond O still from there, and we still have the rest of the molecule, but we gain an oxygen. So instead of having just the H for the aldehyde, we have an OH. So we have OH. So this is the carboxylic acid structure. And we can check if this equation balances, and we can see that we got an R on both sides. We have 1 carbon on both sides. We have 1 hydrogen here on both sides. And there's no difference because there's 2 oxygens on both sides as well. So there's no byproduct here, and this is already balanced. So this is the carboxylic with 1 L acid. If we start off with the alcohol and leave it oxidizing through the 2 steps, we can actually show an overall equation for that overall reaction by combining these 2 steps. So we have the alcohol on the left-hand side of the equation, and we have 2 lots of oxidizing agents. So we have 2 lots of these on the left-hand side. So we have 2 lots of O in square brackets. On the right-hand side, we have carboxylic acid. So have one of those on the right-hand side. And I've also got on the right-hand side a water molecule. So I have one of those as well on the right-hand side. Now, there's an aldehyde on the right-hand side on the top equation, but there's an aldehyde on the left-hand side on the bottom equation, so they would effectively cancel each other out on either side of the equation, so they don't appear in the overall equation. So the overall equation for the oxidation of a primary alcohol to the carboxylic acid is this, and we have 2 lots of oxidizing agents, and this water came from the first step. So we use hot aqueous acidified potassium dichromate, which has the active part being the anion, and this is actually orange to start off with. When it undergoes reduction itself, because as an oxidizing agent it would reduce itself in the reaction, it becomes chromium-free ions, and chromium-free ions are green in colour. So as this reaction occurs, you will see the colour change of orange to green. So we can do an example of a specific alcohol like ethanol, and we can oxidize it in acidified potassium dichromate or aqueous acidified potassium dichromate. So here's the dichromate, and the aqueous state symbol must be in the equation. We have the protons to acidify the solution. We're going to explain why we need the protons in the second year, but for now, just accept we need to have the protons there. And we're going to heat. And initially, it's going to produce the aldehyde. So in this case, we're going to produce something called ethanol. So we have ethanol on the left, and on the right, this aldehyde is called ethanol. So we replace the OL with AL for aldehyde. So you can have propanol as an aldehyde, you can have butanol as an aldehyde. So that's how we name aldehydes, with an AN as the suffix at the end of the name. So we balance the equation by putting water. The aldehyde then can undergo further oxidation, so we have the ethanol undergoing oxidation again to give us the carboxylic acid. So the name of the carboxylic acid is going to be ethanoic acid. So we take the A of the parent alkane and replace it with OIC, so oic acid, so we can have propanoic acid, butanoic acid, and so on. Ethanoic acid is the compound in vinegar that gives it the sour taste of vinegar. And these reactions basically showing the conversion of ethanol in wine to vinegar. And the word vinegar relates to the word wine. So in French, word wine is vin. You can have aldehydes with two aldehydes function groups, and these are called dials. So you can have, for example, here we've got a dial with two carbons that's based on ethane. So we have ethane as a parent alkane. We take the E off the parent alkane, replace it with Al, and that's ethanol. But because we've got two aldehyde groups, it's a dial. So we take the Al to one side and we put di. Now then we've got a problem here. We've got the two constants following another. We don't like two constants following one another. So what we do, we put an E back in from the alkane, and this is ethane dial. There's no reason to put position numbers, and you think about why we don't need position numbers. So here we have another dial, and again we've got two functional groups here, and they have to be on the ends here, because if the double bond O was here, there's no hydrogen for the aldehyde. We must have it on the ends here. That's the reason why we don't need the position numbers really. So in this case, we've got 1, 2, 3 carbons, so this is based on propane. And then we have an aldehyde, so this is propanol. And because we've got two aldehyde groups, this is a dial, so we put a di in front of the aldehyde, or al, so this is dial. And then because we've got two consonants following one another, we need to put the E back in from the parent alkane to separate the two consonants, so this is propane dial. When we oxidize secondary alcohols, we don't get aldehydes, but we get a different product. So if we oxidize secondary alcohols, we're going to get a ketone, and a ketone has this structure. So I'm going to try to relate it to my original alcohol and keep the O here. And we have the rest of the molecule. And you can see already that the carbon is bonded to 4 bonds, so there's no other atom bonded to this. Now we've got 3 regions of electron density around the central carbon atom. So we've got double bond here, which is 1 region of electron density, then 2 single bonds. So this is better written as a trigonal planar shape. So this is called a ketone. It's pronounced ketone, although it's written as ketone. So often I get people write a Y in there as in ketone, which is incorrect. And this word is related to ketosis, which occurs if you go on an Atkins diet and you break down fats through ketosis. We still need to balance this equation as it isn't balanced yet. So we can look at the left-hand side here. We've got carbon, and on the right we've got 1 carbon. On the left we've got 2 alkyl chains, or rest of the molecule. On the right we've got the same as well. And on the left we've got 2 hydrogens, which are not shown here, so we must have something with 2 hydrogens in. And on the left we've got 1, 2 oxygens. On the right we've only got 1, so you probably guess that this is going to be water. Ketones don't undergo further oxidation, so this is as far as the reaction will go, and there isn't another step. So this is the overall equation for the oxidation of secondary alcohols. So I'll do an example. So here we have a secondary alcohol, propan 2O, We can't use propanol because that's a primary alcohol and that would give us an aldehyde and eventually a carboxylic acid. So we can oxidize a secondary alcohol here, propanol, using our aqueous acidified potassium dichromate, which is orange. We heat it and we will get straight away the ketone. The ketone in this case will look like this. So where I had the OH, that would be gone, the hydrogen has gone, and then we have a double bond between the O and the carbon here. So this is called propanone. So we take off the A from the parent alkane from propane and replace it with ONE, as in the ONE in ketone. So this is propanone. We don't need a position number here for propanone because we only have one possible place the double bond O can go, because if we have the double bond O here, that will be an aldehyde. We then have the water to balance the equation. So here we've got some of the examples of ketones, and I'm going to show you how to name some of these ketones. So the first one here on the left here, we've got butanone with 4 carbons, 1, 2, 3, 4. And again, we don't need a position number for the double bond O here, because if it was on this carbon, it's the same as this one, just rotated in space. If we have the double bond O on the end here, it won't be a ketone, it will be a aldehyde, because you will have the double bond O and the H here, which will make it an aldehyde. This middle one here has 1, 2, 3, 4, 5 carbons, so it's based on pentane. So the parent alkane will be pentane. We take the E off the parent alkane and replace it with ONE, which is the name for a ketone, or the ending for the ketone. And then we need a position number in this case for the double bond O, because this double bond O can be here and it'll be a different compound. So what we need to do, if we need to shift the ONE to one side, we don't need to add any vowels or constants because we've got a constant and a vowel next to each other already. So what we do then, we put a number in between these two parts, and the position in this case is position 3. In either way we count it's position 3. So 1, 2, 3 or 1, 2, 3. So remember, we put a dash to separate a number and letter, put the position number, a dash again to separate a number and letter. So this one here, we've got 2 ketone groups. So what we do, we count the longest chain, which is 1, 2, 3, 4, 5. So that's based on pentane. So we start with the parent alkane, pentane. We know it's a ketone, so we take the E off the end for the alkane and replace it with ONE. Now, because we've got 2 ketone groups, this is not an one, this is a dione. So we're going to write dione. So this is a di for 2, one. And then we need position numbers this time. So this time we have positions 2 and 3, which are the smaller numbers. If I count this side, 1, 2, 3. If I count the other side, I get bigger numbers. So 1, 2, 3, 4. So we've got 3, 4 there. So we want the lowest numbers, which is 2 and 3. So we put pentan. Now, in this case, we can see we've got 2 constants. We've got N and a D. We don't like 2 constants together. So what we do, we put the A from the parent alkane back in, and then we put the numbers in. So we have a dash, separate number and letter, and then it was 2, comma, to separate 2 numbers, 3 dash dione. So this is pentane 2,3-dione. Finally, tertiary alcohols cannot be oxidized by using aqueous acidified potassium dichromate, so we don't need to learn any equations for this one. So we looked at how we can burn alcohols and write balance equations for the combustion of alcohols, which is a type of oxidation. But then we also looked at how we can oxidize alcohols using an oxidizing agent, and we use aqueous acidified potassium dichromate. And we're going to look at, in the next video, how we can set up different apparatus to control what products we get for the oxidation of primary alcohols, because we can get aldehydes or carboxylic acids, and there's a way of controlling the yield of the desired products if we wanted to, for example, make more of the aldehyde rather than the carboxylic acid. And then these 2 reactions are really just revisions, so I'll cover those later as revision.